Alright guys, today we're going to do note card 31, which is called absolute extrema on an interval. Okay, we're going to talk about this thing called the extreme value theorem. So before we get into the note card a little bit, I want to make a couple pictures for y'all so you can understand this a little bit better. Alright, so here's what, let's just take a look at a graph real quick. Suppose I have some function f of x. But we only want to look at f of x over a certain interval, okay? Only from the interval a to b. So here is what the extreme value theorem says, or what we call the EVT. As long as f of x is continuous over the closed interval a to b, as long as f of x is continuous over the closed interval a to b, which means that these points have to be defined, okay, there is an absolute maximum value and an absolute minimum value over AB. Okay. So what does this mean? This absolute maximum and absolute minimum. Okay, so what we think of when we say absolute maximum, that's the high point. There's a high point somewhere in there. So here over this interval, what's the biggest y value? Well, here the absolute maximum value is right there. This is the absolute maximum value. It also guarantees, this theorem also guarantees that there's an absolute minimum, okay, a low point. There's a y value that's less than all other y values. Less than or equal to, I should say. Okay. So here, this is the lowest it gets. That's the smallest y value. And here's the biggest y value that it gets to. Okay. Now, as long as this function is continuous, by this theorem, I know there's a high point and a low point along this curve over this interval. Okay. The EVT does one more thing for us. Okay. It also says that these absolute extrema, okay, we call these things, we call the absolute maximum the high point and the absolute minimum the low point. Okay, they're called extrema because they're more extreme than all the other y values. They're going to occur on the endpoints or at critical values. And we'll learn more about critical values as we go on, but critical values are where the derivative equals 0 or where the derivative is undefined. Sorry. So if I think about this, if I think about endpoints, this could be the locate, that's an endpoint between A and B. Remember, it's a closed interval. All right. An absolute maximum or minimum could occur there. And there's also two other critical values. There's a critical value here because the derivative there, or the slope of the tangent line, is 0. And this is also a critical value. Because right there, the derivative is also 0. Okay, so what the EVT does for us, it tells us as long as we have closed endpoints, we're going to have a high point and a low point, and where those are going to occur is either on the endpoints at this value A or B, or at these values, which we can call C1, C2, because these are the critical values. Okay, so why is this useful? Why is it beneficial? Because it kind of narrows down all the possibilities, all the numbers between A and B to simply 4 numbers that we have to test out. Okay, and as soon as we figure out what these X values are, you can just plug in all these different values. Okay, so you could plug in f of A, you could plug in f of C1, you could plug in f of C2, and you could plug in f of B. And you'll get a number out, okay, each time. And to figure out which one's the maximum, okay, figure out which one's the maximum, which one of these 4 numbers that we would get out, which one is the biggest. And for this particular curve, that one would be the biggest because it's the high point in the graph. Okay, so this would be, this number right here would be the absolute max. Okay, and then when we get all the numbers again, all right, this f of C2, okay, that y value, we would get a number out, and that's going to be the low one, because we would compare these 4 numbers and ask ourselves which one's the smallest. So the EVT is very powerful, okay, but it's got to meet these 2 conditions. It's got to be a closed interval, okay, so these have to be filled in dots, they can't be open circles, okay, and the function has to be continuous. Let me kind of show you another example why the closed interval makes a difference. Okay, so for instance, if you had a graph like this, okay, if you had open circles instead, all right, this graph does not have an absolute minimum, because you might think that this is the absolute minimum, but we don't actually ever get to that y value. We get really close to it, but we don't ever actually hit it. So there's no absolute minimum. Okay, so I just gave a counter example on there's no absolute minimum. Same thing here on this y value here. We might think that that's the absolute maximum, but we're actually never getting there. Okay. Now, if you think about this graph right here, here we do have an absolute maximum and we do have an absolute minimum, but we're not guaranteed it, because like in this graph, okay, if this endpoint and this endpoint are open circles, what about if they were going to be the absolute maximum? So the only way we're guaranteed to get an absolute maximum or minimum is to have these endpoints filled in. They have to be closed circles or filled in circles. Okay. And the other requirement of the theorem is that it has to be continuous. Okay, so let me show you a counterexample where we would not have an absolute maximum. If the graph is not continuous, all right, if I start the graph here, okay, this is the A value and this is the B value. Let's fill in that point. In this particular graph, if the graph is not continuous, you can see right there that's an open circle. So there is no absolute maximum. Okay. There is no absolute maximum. There is a minimum. This is the absolute minimum. We never get a y value smaller than this. Okay, but we're not guaranteed it. And just like this, we're not guaranteed it if it's not continuous. All right, we could get it. All right, if I take that same graph and I fill in that circle. Okay, I mean, here we do have an absolute max. And we do have an absolute min. Okay, but it's not guaranteed. The only way it's going to be guaranteed is if, again, the endpoints are filled in, they're closed circles, all right, and the function's continuous over that entire interval. That's the only way we're guaranteed to get a high point and a low point. So going back to the note card, let's look at it. And sometimes absolute maxes and absolute mins are called global maxes or global mins. Okay, global max, global min. And a number is a global min if the y value is smaller than all other y values in that domain. Okay, and the number is an absolute max if the y value is bigger than all the other y values for all numbers in the domain. So let's do this note card. In this note card, there's no associated packet with it. So it says, using the graphs of the following functions, determine whether the extrema, okay. So here when we see the word extrema, they're talking about maxes and mins, or absolute maxes and mins. Okay, absolute maxes and mins, whether they may not exist, are located on the endpoints, or if they're located in the interval. Okay. So on the first question, they're asking us to use our calculator, and they're telling us the interval to look at, A to B. All right. So I'm going to go ahead and type that in. Negative x to the fourth minus 3x cubed plus 5. Okay, and I want to focus that in on the interval from -3 to 1.5. So I'm going to change my x-min and x-max to -3 and 1.5. I'm going to scale it by ones. And then I don't know how high or how low it's going to get, so I'm going to go zoom 0, zoom fit. Okay, so that's the graph. If I want to change this a little bit, okay, we can maybe make this go up to, I don't know, 200, just to see it a little bit more clearly. Okay, so that's what the graph looks like. So let's ask ourselves, does it meet the criteria here? All right. This function is a polynomial function. We know that polynomial functions are continuous. Okay, so it is continuous. Okay, it is continuous. Okay. Now, what's the low point here? Okay, what's the low point of this graph? You got to remember there's a filled in circle right here, and there's a filled in circle right there. Okay, so here, the absolute minimum is on the endpoint. Is on the left endpoint. Okay, so here, let's figure out what f of -3 is. Okay, so if I hit trace here, and I type in -3, it gives me a y value of -6,556. Okay. And if I just hit trace here again, and I follow this up, it looks like as I'm going along, All my y values are negative. Then they start getting positive. And right there at 0, it's 5. Then it looks like it keeps increasing. Looks like the y values keep increasing. Okay, so let's figure out what it is at 1.5. There it looks like the y value is 56.257. So the absolute max is on the right endpoint. Okay. This is the value of the absolute min. This is the value of the absolute max. Okay. So here in this particular case, it is located on the endpoint. This one, B. The absolute extrema are located on the endpoint. Okay. So let's do the next problem. It says y equals x squared plus 1, and they want me to graph this by hand. We should know what this graph looks like. Okay. X squared plus 1 is a parabola. It's the parent parabola shifted up by a unit. Okay. So if we think about this graph, it should look something like that. But now they want me to focus in just on the interval 0 to 2. Okay, so if I plug 0 in here, it gives me a y value of 1. Now this has a bracket, which means there is a closed circle. If I were to plug 2 in here, 2 squared is 4, plus 1 is 5. So 1, 2, 3, 4, 5. All right, but here, this is an open circle because there's a parenthesis there. So just the values I care about are x is 0 to x is 2, but not including 2. So in this case, 1 is the absolute minimum, but because we have an open circle here, there's no absolute maximum. All right, it's not continuous over a closed interval, all right, because of this thing right here. So because there's no absolute maximum, all right, it doesn't exist. So A is correct in a sense. But the absolute min, there is an absolute min because of that closed-in circle. There's no y value is smaller than 1. Okay, so the absolute min is located on an endpoint. Okay, so here it's A and B because the absolute max doesn't exist, but the absolute min is still located on an endpoint. So B is kind of right. A is kind of right, B is kind of right. Extreme value theorem, very, very beneficial. So when you're looking for absolute maxes and mins, we have to focus our attention on the endpoints. And then if sometimes we get a high point or a low point inside the interval as well. All right, but we'll get into that a little bit later. So that's all there is to this note card. Okay, so I would really commit to learning this theorem and knowing it well. Okay. Very, very useful and very, very helpful theorem, but you have to know the conditions. It has to be continuous over a closed interval. Okay, so the interval has to be filled in circles on the end, and it has to pass your pencil test. Okay, no gaps. And that's going to do it for this one.